Welcome back to the exam walkthrough. We're going to be going through 2024 June electric field question. This is going to be question number 17. So you can go through the question and try it yourself. So it says scientists are developing safe methods for removing old satellites from orbit. Some scientists plan to use electrostatic forces. A spacecraft will fire a beam of electrons at a satellite. This will give the satellite a negative charge and the spacecraft a positive charge. There will be an electrostatic force of attraction between the satellite and the spacecraft. The spacecraft will then move away, taking the satellite with it. And then it shows the diagram of the electric field around spacecraft X and Y when they have equal and opposite charge. You may assume that the spacecraft and the satellite are both spherical and have same diameter. And then for the first part of the question, they tell you add dashed lines to the electric field diagram to show the equipotentials at intervals of equal potential difference for 3 marks. So your equipotential lines will look something like this. Okay. Now, before I go on to further explain this, let's get some things cleared. So, an equipotential line is a line along which the electric potential is constant. The potential for a point charge is the same anywhere on an imaginary sphere of radius r surrounding the charge. So if you look at these 3 points, this point, this point, this point, all of these points have the same electric potential. If you look at this point, and this point, all of them have the same electric potential. The reason is because this distance r, this distance r, this distance r, this distance r here, this distance r, this distance r, they're all the same thing, right? In this example, they're all the same. In this example, they're all the same respectively. So there are some equipotential lines conventional rules that you have to know. The first rule is that the equipotential lines are always perpendicular to the electric field strength and the electric force vectors. The second rule is that the spacing between the equipotential line shows us the strength of the electric field. A wider spacing of equipotential lines indicates a weaker electric field because the same work is done over a larger distance. The third rule is that in a uniform electric field, equipotential lines are straight, parallel, and equally spaced. And then the last rule is that for equipotential lines of the same potential value, a larger equipotential radius indicates a larger magnitude of charge. So these are 4 key rules that you have to keep in mind. Now let's go back to the question. Now the first thing, I hope you've already studied how to draw these lines or at least have a bit of clue now. Okay. So the first thing that I want to explain is the spacing. Okay. Let's explain the spacing of the lines. Why are the lines closer here? Notice the distance between the lines is much more compact here. The lines are much more dense here than they are here. Notice the spacing is much more on these 2 sides, right? So you can notice I've labeled the 3 areas we're looking at. Now, more spacing means that there's a weaker electric field, and less spacing means there's a stronger electric field. That means the electric field is weaker in these 2 places and it's much more stronger here. And now I'm going to show you why that's the case. Okay. So let's take A for example now. Now A will be a test positive charge, for example. It's a positive charge here. Okay, remember when we draw when we consider electric fields and their direction, we're always going to take by considering the positive charge, test positive charge. Okay, so imagine there was a positive charge here. That positive charge would be repelled away because of this positive charge here. Let's call it Q1. Let's call the other one Q2. So it will be repelled away by the Q1, but it will also be attracted by Q2. Now since the distance from point A to Q2 is a lot more, so the electric field strength will be weaker. So this is E1, E2. So when we add both of these fields, we should get a E resultant. Now that will be a bit smaller, okay, because both of the electric field vectors are in opposite directions. Okay, now let's talk about point B. Now, when we look at point B, we can notice it's going to be, again, test positive charge. It's going to be repelled away by the charge Q1 and attracted by charge Q2. So we can see E1 and E2 are going to add up. Now let's look at point C. Again, attracted by the Q2 charge and repelled away by the Q1 charge. Again, both of them will add up. Okay, now let's look here. So we're going to get the resultant field at B, resultant field at C. And then let's put the A here as well. Okay. Now let's look at this one. Point number D. Again, D test positive charge. It will be attracted by the negative charge and repelled away by the positive charge. Okay, but the repulsion will be much more smaller here. So this is E, let's call it E1, E2. You can just say that and then just add both of them and we get ERD. Actually, this will be E2 and this will be E1. Okay. Now, we can see that the electric field strength here and here is much less than B and C. You can see the B and C, we're adding two values. Okay, and they're both in the same direction. So they're going to add up to give you a bigger number. Here, opposite direction, smaller number. One will be positive, one will be negative. So that's why the electric field strength here is weaker and here it's much more stronger. So I hope that first part is clear. Okay. That's why we also draw this straight line in the middle as well. Okay. And then we make the field lines dense here and less dense here. Okay. I hope that is clear. Now, another significance, which is basically the next part of the question, is that label the equipotential line that represents 0 volts. And the equipotential line that represents 0 volts is going to be this straight line over here. This is going to be 0 volts equipotential line. So at this point here, now we're looking at the potential, electric potential. Now I want you to forget the electric field. We're looking at electric potential now. For electric potential, let me just draw the graph that will help you understand. So this is a positive and negative charge, same thing. On the y-axis, we have the electric potential, and on the x-axis, we have the distance. So let's draw individually the graphs of both of these charges. They both have the same magnitude, so let's just start it like this. And then it should go something like this. Okay. This is going to be positive region. And then for the negative charge, it's going to start from the negative region. And it's going to go like this. Okay. Right. That's how both of their graph would be, right? I'm sure you have drawn these graphs. Now what I'm going to do here is we're going to be adding both of these graphs up, which means, let me just do it like this. Yeah. So let's say this is point A. Okay. Point A. What we're going to do is we're going to add this and this, the two values together, and we're going to get another graph. Okay. And then we're going to add these two. So we're going to add all the values and we're going to get a resultant graph. Okay. Let's say you get 2 here, you get -1. So you add both of them, you get 1. So similarly, we do it for every single point. And the graph that we end up getting looks something like this. Second. Okay. The graph we end up getting would look something like this. Something like that. It's not the best, but yeah, it would be something like that. Okay. And my main point here is that there would be a point at which the potential is 0 volts. Okay. That's the point that is represented by the straight line in the middle. Okay. So now we're looking at the electric potential, and I hope that's clear. Don't mix it up with the electric field. Okay. So I hope that is clear. And we've also solved the next part as well. Okay. I think that's all I'll keep for this video. I'll move the next part to the next video.